I guess, the opportunity to speak here. I know that, well, we're not actually in Matrix, but this is a Matrix supported event. So I'm pretty sure this is a building on the Creswick campus at or just behind Matrix House. I'm pretty sure it is. But anyway, so yeah, this is joint work with some people that may be very familiar to some in the audience. So this is Jan de Geer and Michael Wheeler. And this is also joint work with Daniel Remenick, who's in Chile. Yes, okay. So I guess we heard a bit about in the last talk about determinantal point processes and Pfaffian point processes. So I'm going to talk a little bit about some descriptions of some new Pfaffian point processes that we've obtained. And I'm going to sort of relate this to a very, very well-studied story in physics literature, as well as some probability theory, which is this topic of KPZ universality. And I think there's quite a nice story to tell here about sort of connections with some integrable processes. These integrable processes, I guess the most notable one that I'm going to be talking about today is the TARSIP. From this, I'm going to be looking at some extension of the most common version of TARSIP studied, which is this half-space TARSIP now, which is going to be some system with now an open boundary. And we're going to see some sort of reduction from so we're going to see some sort of extension of a determinantal structure to some sort of Pfaffian structure with an open boundary. And from this new Pfaffian structure, we're going to be able to sort of compute exact current distributions. And we're going to be able to relate to some problems associated with skew orthogonal polynomials. And this is sort of related to classical orthogonal polynomial theory. Okay, so to start with, I'll give some sort of outline, some sort of outline of some physics motivation that I want to consider. So let's consider a model where I have blocks falling randomly into certain sites associated with integers. So here I'm just going to imagine some dynamics where I've got a certain number of columns, and I'm going to allow blocks to fall independently, and they're going to be falling randomly on each column. And the dynamics of the block is that there's going to be, the dynamics of the falling is that there's going to be some sort of completely uniform distribution based on, so the blocks can fall into any of the columns completely independently with a uniform distribution. And there's no sort of dynamics here, so each column is independent of each other. So there's no sort of dependent dynamics between neighboring columns. So I'm going to associate and define a height function in the obvious way. So this height function is going to be a random variable, is going to be a function of random variables. And as expected, the height function is going to grow linearly, or we expect it to grow linearly. And interestingly, when we want to sort of measure against the linear growth, we want to measure fluctuations about this linear growth. So if I compare the height function to some sort of function which is linear in time, I'm going to expect to see fluctuations of the order t to the 1/2. So this is consistent with this is consistent with what we would expect from some sort of Gaussian distribution. So the columns here are going to be independent, so there's going to be no spatial correlations. So this is completely consistent with predictions from the central limit theorem and what we would, I guess, call Gaussian universality. So the central limit theorem means that in many, many different places, I'm going to expect to see the Gaussian distribution function pop up. And that's exactly what I'm going to see here. So let's consider a slight extension of this model where now I'm going to have similar block falling dynamics, but now when a block falls down, it's going to stick to a neighboring, it can stick to a neighboring column. So this block here is going to fall down and it's going to stick to this site down here, which is because the column next to it on the right has an associated height. This block here is just going to fall directly onto this column, and you can extend the dynamics in this way. So this stickiness is going to really endow this model with very, very different behavior. So we're going to firstly expect that the height function is still going to grow linearly. However, now if I measure against this linear growth, then I'm going to expect to see fluctuations now of the order t to the 1/3. So this is perhaps somewhat unexpected to have this fluctuation exponent. And now because of the stickiness as well, I'm going to have non-trivial spatial correlations of order t to the 2/3. So these exponents are very, very different from what you would expect from the central limit theorem, and indeed they are very different. And but what you see if you do enough experiments is that we see these kinds of exponents pop up in multiple places across many, many different, I guess, random growth processes. So these collections of random growth processes which display these exponents are called the KPZ universality class. So in particular, I'm going to expect to see t to the 1/3 fluctuations about some random linear growth. And I'm going to see this across many, many different models depicting some kind of random growth process. So this idea of universality here is a really, really powerful result, as we'll see soon. So this KPZ universality is not really restricted to, I guess, it's not really restricted to models which are toy models, like the models we just saw. You can genuinely see this type of behavior in the real world. So here are some examples. So I've got here an experiment where I've got some sort of cancer cell growth in some sort of controlled condition. And I'm going to expect that this cell colony is going to grow sort of radially with a radius growing linearly in time, but there's some sort of roughness to it. And this sort of dynamics is going to be indicative and have this, we're expecting this type of process to occur, to have sort of t to the 1/3 type fluctuations. Equivalently, I can also take a piece of paper and I can, on my sheet of paper, I can light one edge on fire. And what you're going to see is that this fire is going to move down the page. But this is still going to be a random sort of growth process. And this is what we see in this picture where I have some sort of fire front on a piece of paper growing in time with some sort of rough dynamics. And then if I compare down here, this Eden model, which is some sort of idealized version, I guess, of this cell colony growth, where I have this sort of random surface dynamics. I don't care too much about it. But the point is that the radius is going to grow linearly. And I'm going to expect to see raised sections or lowered sections. If I zoom right into this red square, I have a raised section, and this raised section is going to be roughly of the order t to the 2/3, and the height of this is going to be of order t to the 1/3. So these are examples of KPZ universality, sort of observed in sort of real-world experiments, but also on more idealized computer experiments. So just a bit of a word on the philosophy, I guess, of this field of integrable probability. So the goal in statistical mechanics as a discipline is to start with some sort of microscopic particle behavior, and we want to scale this up to sort of observe some sort of macroscopic properties about a large system. Okay, and integrable probability is when we want to deal with using exact algebraic results that we know occur microscopically, and we want to scale that up and sort of look at exact distributions, which really means looking up at macroscopic sort of observables. So if I look at some sort of if I want to study the KPZ class, well, what I want to do is I want to come up with some sort of integrable model or some sort of exactly solvable model which lies within this class. So there's been many, many cases of this where over the last sort of 25 years, where we've seen integrable models that we've been able to scale up, and we've been able to sort of observe the really famous and typical KPZ exponents. Okay, so one such model here that I want to consider, which will be the topic of the rest of this talk, will be this asymmetric simple exclusion process. So this is some sort of random particle process where I imagine some kind of 1D lattice, and I'm going to put a selection of particles on this, which I'm going to indicate by these red dots. And these red dots, I'm going to allow them to move randomly in time. And they're going to have, they're going to move, either they can jump to the left with some rate q, or they can jump to the right with some rate p. But the catch here is that a particle can only jump into a site if that site is free. So this particle here on the left can jump either to the right or to the left, but this particle can only jump to the left because its neighboring site on the right is occupied. And the same goes for this particle, where it can now only move to the right. So this sort of behavior, while the model is still simple enough, this sort of behavior is going to allow us to study some sort of more complicated interacting particle dynamics. Okay, but in particular, my interest in this model is really because the RCEP is Yang-Baxter integrable. So it's really this means that I can compute many, many different quantities of interest. And I can compute these exactly. And this is going to follow from some sort of underlying solution to the Yang-Baxter equation, which is hidden in here in the dynamics of this model. And importantly, I should probably point out that this RCEP, if you're interested in quantum systems, is very, very closely related to this so-called Heisenberg XXZ spin chain. How does this RCEP relate to KPZ universality? Well, you can imagine some kind of particle process, like I've got 4 particles here, and associated with the particle positions, I'm going to draw a height function, which means every time I've got a particle, I'm going to draw a downslope, and every time I've got no particle, I'm going to have some sort of upslope here. And I'm going to drop some sort of connected path, some sort of connected path here, but really the particle dynamics of the ACEP here are going to correspond with the random growth of this process. So if this particle is going to move to the right, well, this trough is going to move to a roof like this. And if this particle moves to the left, well, this roof is going to move to a trough. So this is, if you imagine scaling this up with a very large system, you're going to see some sort of random growth dynamics from this model. So I guess a very, very simple version of this model, which really displays some sort of very nice algebraic properties, is the so-called totally asymmetric simple exclusion process, or the TARCEP. So I'm going to obtain this when I set p to 1 and q to 0. So what does this mean? Well, this means that particles can only move to the right. So here's the same sort of dynamics that I had before. So here's the same configuration I had in my diagram before, but now particles can only move to the right because I've set the rate hopping to the left to be q. But importantly, this is still this is still a stochastic process. So this means that this particle here cannot move at all until this particle moves off to the right. Okay, so here's a simulation of this model. So I'm going to start with, so this is the time direction vertical, and I've got some sort of tracking the positions of particles. And so here's a space-time diagram. So if I have, it looks like 20 particles here initially all next to each other, then as time goes on, then I'm going to expect that, well, this particle can move very far into the lattice. And yeah, you see this sort of complicated sort of queuing behavior because of the nature of the dynamics. But yeah, so this is going to be the focus of the talk. Okay, so why are we interested in this model? Well, here's one of the very, very nice algebraic properties. So we're going to be interested in computing the transition probability. So this means I'm going to be putting n particles on some infinite lattice. So this lattice is going to be the integers. So the positions are going to be denoted by the positions of particles are going to be denoted in these vectors x and y. So x is going to consist of n positions, and so is y. Now, here's a very famous result, is this the transition probability for the TARCEP, which says that, well, the transition probability, if I'm initially in some state y at time t equals 0, and what is the probability that in some time t, I move to a new state x? Well, this is given exactly as a determinant. So this determinant here is going to be an n by n determinant, where n is going to be the number of particles here. And r, this function that appears inside the determinant, is going to be given by this simple interval. So you might wonder, there's sort of 2 ways of looking about this. You wonder, well, why on earth should a model which looks as simple as this, why on earth should this have such a horrible formula? Why on earth should this transition probability have such a horrible formula, where I've got some sort of what looks like a relatively complicated integral sitting inside some sort of relatively complicated determinant? But I think there's another way of looking at this, which is that, well, we've got 2 ingredients here. We've got a determinant, and we know that determinants have very nice properties, as we've seen in some of the earlier talks this afternoon, where I can sort of use all linear algebra properties. And equivalently, if I want to take some sort of scaling analysis, I've got some sort of integral. So perhaps there's some way of using an integral to do some sort of steepest descent analysis. So that's sort of the idea we want to do to study KPZ universality. But unfortunately, Schutz's formula, this determinant, is not yet in the right form. So in order to study some sort of asymptotics, I really want to take n to be large. So that's going to mean that I want to take a very, very large size determinant, and that's not really appropriate for this sort of yeah, the Schutz's determinant is not really yet in the right form. So there was some really nice work, some amazing papers by Tomohiro Susomoto, and then a follow-up paper by Borodin, Ferrari, Preyhofer with Susomoto as well, where they were able to use the properties of the determinant to define some determinantal point processes for this TARSEP. And this really meant that these authors were able to compute the current distribution of the model. So what does this mean? This looks a little bit confronting, but all this probability I've got on the left here means is that I'm going to pick any particles that I want, and I can pick the probability that any of those particles, any number of them, have crossed any points I choose on my lattice. And they underwent this procedure where they've gone from Schutz's determinant to this joint distribution, and this joint distribution is going to be given in the form of a Fredholm determinant, which is going to be in a suitable form to do KPZ analysis if you haven't seen them before. And this kernel is really written in terms of two functions. So the first function is this known function psi, which I can start my analysis with. I'm not going to write it down, but it exists. The second function that I need is a family of polynomials, which I'm going to call phi. And these polynomials are going to be implicitly defined in my analysis. I don't have an exact formula for them, but I know that they're going to satisfy this orthogonality property, which means that this process about this problem about now computing this explicitly this joint distribution as a Fredholm determinant is now converted into a problem of classical orthogonal polynomials. So this was, I think, was a major achievement. The orthogonal polynomials that you actually consider are going to be determined by your initial conditions, which is then going to have an impact on the KPZ universality we're going to consider. So I can scale, as I mentioned, I can scale my Fredholm determinant, and this means I can observe and prove expressions exactly like this, which is where if I imagine exactly like I had in my simulation, I'm going to imagine having sort of a certain number of particles adjacent to one another. And if I track the position of one of these particles and I measure this against something which grows linearly in time, and I make some sort of correction, and I want to measure the size of this correction of order t to the 1/3, then it turns out that this correction of order t to the 1/3 is governed exactly by this Tracy-Whittem GUE distribution. So this is not what you would expect if you were looking at some sort of Gaussian distributed system, because the Tracy-Whittem GUE distribution is not, we saw another, I think it was the Genebra unitary ensemble in the previous talk. The Gaussian unitary ensemble is a distribution from random matrix theory, which is associated with the largest eigenvalue of some underlying random Hermitian matrix. But importantly, this distribution function itself, the Tracy-Whittem distribution, is not Gaussian. So if I change my initial condition, I'm going to change the sort of non-Gaussian distribution function I exhibit here. So I can also observe things like GOE and other non-Gaussian distribution functions. But really, this is going to justify that this TARSEP problem, this lies within the KPZ class. So this is perhaps not the best example, but there's all kinds of other examples of using the exact procedure I outlined earlier, this Borodin-Susomoto procedure where I compute these orthogonal polynomials, and this is going to relate to this observing different distribution functions here. The main topic of the talk and the main area where the new research that me and my collaborators have been working on is now this asymmetric simple exclusion process in the half-line. So I outlined this very well-told story about models in the full line. So these are models without boundaries. And I now want to sort of see what happens, what is the story on the half-line. So the half-line dynamics are the same, where I sort of have some sort of infinite lattice which stretches across to the right with infinitely many sites. And the dynamics of particles are really the same in the bulk here, but now particles at the boundary on the left, so this is at site 1, can move in. I can generate new particles with rate alpha, and particles can leave with some sort of rate gamma now. So the Yang-Baxter integrability structure that I observe in the full space TARCEP, this is really going to extend to this open boundary RCEP, where now I also, in addition to the Yang-Baxter equation, I'm also going to have this equation called the reflection equation, which endows this sort of model with integrability in the same way. But the usual techniques of integrability that I would want to use to study this model are much more difficult. So these are techniques like coordinate beta ansatz. So these are made technically more difficult, and this is precisely because my particles are no longer conserved. So the topic of this talk and the rest of the talk that I want to outline is going to be the limit q to 0 and gamma to 0. So this is what I'm going to call my half-space TARCEP, so totally asymmetric version. So this is the half-space TARCEP where particles can move in at rate alpha. So I still do not have particle conservation because particles can still enter the system. And once in the system, they can only move to the right. So these are the dynamics of my process. So there's been some work on this. This is not a new model. It's considered a sort of a cornerstone model for studying KPZ universality in half space. So here's an example of some results where people, this group has managed to compute the joint distribution for this model, and it's been computed as a Fredholm-Pfaffian. And we'll hear a little bit more about Pfaffians. So I want to but this is restricted to the case of empty initial conditions. So I want to see what I can do with some sort of more general classes of initial conditions here. Yes, so this sort of distribution function has been used to study, so this sort of current distribution function has been used to study KPZ fluctuations at different points in the lattice for different values of alpha. And it's a very, very nice story. And we want to really try and contribute to this story. Okay, so here is the first main result of the talk, which is the transition probability. So consider the half-space TARCEP, and I'm going to imagine some sort of empty initial condition. And if I start with an empty initial condition at time t equals 0, what is the probability that I end up with, say, particles in at position, sorry. What is the probability that in some time t, I end up with a certain number of particles, so n particles in positions nu? Well, this is given by e to the negative alpha t, so some sort of overall constant, times a single Pfaffian. So here nu is going to have n particles. This is really like my position x. It is going to have n particles, so this is going to be an n by n Pfaffian. And here the kernel of this Pfaffian is this function q, where this function q is really now given by this double integral. So if you're not familiar with Pfaffians, you can just imagine taking an even dimensional skew symmetric matrix. I want to take its determinant, and what you realize is that this determinant is a perfect square. So I just take the square root of the determinant. So if you're unfamiliar with Pfaffians, you can just imagine the square root of the determinant of a skew symmetric matrix. So this result here, where this transition probability from an empty initial condition to some sort of populated condition is given by an n by n Pfaffian, well, this sounds familiar. And this is really an analogous to Schutz's determinant for the full line TARCEP, where I had an n by n determinant. Well, now I've got an n by n Pfaffian. So yeah, this formula, because Pfaffians, you need to have some sort of underlying even dimensional matrix. But yeah, there's an analogous version if you want to consider odd n as well, but I don't have time to talk about that. Okay, so what can we do with this Pfaffian now that we have this? Well, here's an example of some kind of recurrence relation. So you can sort of manipulate by taking infinite sums on the arguments of this function q. You can manipulate these indices. And what this is going to allow you to do is it means that this transition probability I had earlier, well, this can be written as now as a sum over Gelfand-Settlin patterns. So Gelfand-Settlin patterns, if you're not familiar with it, it's some sort of combinatorial object. It's some sort of triangular array with some rules. But really, I can now, what this means is that I can write this transition probability as some sort of sum over some combinatorial object of a Pfaffian. And this Pfaffian is slightly different. It's now given by this function psi. But importantly, this result is going to allow us to define Pfaffian point processes. And there's a bit of work involved in this. It's the work is really outlined and following this procedure given by this in this wonderful paper by Borden and Rains from about 20 years ago. But yeah, you can define a Pfaffian point process from this. And this is sort of in complete analogy again with what we saw for the full line determinantal point process. Okay, so what can we do with this now that we have the Pfaffian point process, which I haven't really outlined here? Well, I can now compute a joint distribution. So what I'm going to do is I'm going to start with an empty initial condition, and I'm going to consider the probability that certain particles have crossed certain points, exactly like what we considered in all the other examples we saw. Except this time I'm going to have some sort of conditional probability distribution. So I'm going to condition that the number of particles in my system is n. So I can compute this joint distribution, which is conditional on the number of particles in my site. And what we find is that this is given by, instead of a Fredholm determinant, I started with an n by n Pfaffian. What I end up with is a Fredholm Pfaffian. So the Pfaffian that I showed earlier, this n by n Pfaffian, is again not really in the right form yet to consider KPZ analysis. But what I can do is I can now potentially do some sort of asymptotic analysis here on this Pfaffian. So what is the kernel here? So the Pfaffian depends on this kernel. The kernel is dependent upon some initial function psi, which I am not going to write down, but it exists. But it's also dependent now upon this implicitly defined family of orthogonal polynomials. So I'm going to call these functions psi, but these orthogonal polynomials are now going to be skew orthogonal polynomials. So that means if I've got some sort of inner product here, and I take an odd function, an odd polynomial, and an odd polynomial, or I take an even polynomial and another even polynomial, well, the inner product is 0. So these polynomials are all orthogonal. But then if I take an adjacent odd and even polynomial, well, they're going to give me 1. Otherwise, they're also orthogonal. So this is now converting this joint distribution. Rather than going from a joint distribution to an orthogonal polynomial, I take my joint distribution on the half-space Tarsep, and this is now given by this skew orthogonal polynomial procedure. So this is now the skew orthogonal this is the skew biorthogonalization problem that we have to outline. And it is technically quite challenging. So I'm just looking at the time. I think I'm almost out of time. So maybe I'll just quickly mention, I guess, the whole motivation for this problem was that, well, there has already been some work on the full space Tarsep for empty initial conditions. Well, what happens if I want to extend this? So I can consider some sort of a initial condition here where I now start my system with, let's say, m particles, subject to some technical constraint. And if I start with m particles, well, I can extend the transition probability I had earlier of measuring my joint distribution. And I can now calculate the transition probability as a Pfaffian over some sort of block structure. So Q is exactly the function I had in the empty case. And R is actually sort of a rectangular version here of the kernel I observe in Schutz's determinant. So this is going to allow us ultimately to extend the Pfaffian point process procedure that I had earlier. And if I can just make one little remark, the work I've sort of presented here on the half-space Tarsep is actually, I can regard this as a generalization of what's occurred in the full space procedure. So if I set alpha to 0 in my half-space Tarsep, I actually just recover the dynamics of the full space Tarsep. So what this means is that if I set alpha to 0 in this transition probability above, well, I end up with this sort of block structure. And this reduces exactly to this determinant over R, which is nothing but Schutz's determinant. So a lot of this procedure that we're doing here is now sort of extending this determinantal, really well-studied story, and it's going to extend this now to some sort of Pfaffian procedure. Anyway, I'm out of time, so I better stop there. But yeah, thanks for the opportunity and thanks for coming along.